Hi, in this video I'm going to take you through what is inside of the ChipSHOUTER kit and how to use it a little bit. So we take a look, just comes in a box like this, and we're going to be connecting it to some equipment, so that's why I've got a scope in the background and we'll pull out some other stuff. And basically when we open this thing, what you can see is there's a few things right away, right? So there's a user manual for how to use it. Surprise, surprise. And it also goes over some of the serial interface and stuff like that. From there, we get into a bunch of little boxes. And so we'll kind of go through each of these a little bit in sequence and then take a look at how to actually use this thing and some of the more advanced features. So this little box here is simply the main ChipSHOUTER unit. So there you go. So you get a little sort of box to store it in, and you can see it's pushed in here, and that's kind of what it looks like. So let me just move this out of the way here and pull that out. Okay, there we go. So there's the main ChipSHOUTER unit itself, and what you have here is basically you've got a some manual controls on the front. So this is just kind of for like a little bit of general usage, almost playing around. Most of the time you're going to be using there's a cable that plugs in here that gives you a serial interface and also a Python API. And there's also a hardware trigger at the back here. There's this sort of funny, you'll notice like this hex bolt or recessed bolt that can come out. This is actually an inlet for adding airflow. So if you're using this thing with really high repetition rates, it tends to heat up a little bit. And basically what you're seeing is that in order to help cool it, you can actually inject just air. So from like even an aquarium air pump you can use will be enough to help quite a bit. And you can go all the way up to like filtered shop air if you need, really high repetition rates. And the other side here is basically where the various probes are going to plug in. You'll notice the SMA output actually has a tip saver. So there's another SMA sort of female to male right on the end here. And this is actually to help protect the output. So this SMA output is soldered into the PCB internally. So to make sure you don't accidentally, if you like nick this one, you don't want to, it becomes a very expensive repair. This is basically built in to have this sort of tip saver right here. So what's on the next box? So the next box in here is this victim board set. So if we take a look at that guy, what you'll find is two different targets. So as part of ChipSHOUTER, it's designed to help you sort of understand how all of these attacks work. So the first one is what we call a simple EMFI target. And if we pull that out here, what you'll see is this is actually basically this really basic target where there's a microcontroller running sort of this for loop in here, and it's always comparing the results of the for loop with what it expects the results to be. So if the results are correct, it actually blinks this run LED. So every time it's got a correct result, it blinks run, and if it's incorrect, it's going to blink this fault LED. When things go wrong, it also will blink a reset LED. So what we want to try to do is we want to try to insert faults without resetting the device. So if you sort of have the tip attached to the ChipSHOUTER, you'll be able to do that, and it just runs off a little battery pack here. This board goes to sleep, so to save your attached battery, it goes to sleep after I forget if it's 60 seconds or something like that. Basically what you'll see is that it'll stop blinking, and you can either reset it, or there is a physical power button, so you should turn it off physically if you're not using it for quite a while. The second board in here, so this is this Ballistic Gel Target. What this guy is doing is this guy is actually giving you a little more sort of scientific capabilities for your fault injection testing. And what you have is there's a large SRAM chip. Let's put that right side up for you. So on the left side is a large static RAM chip. And on the right side is a microcontroller that downloads a pattern to this static RAM chip. And by inserting, basically you put a random pattern here, we'll insert a fault with the ChipSHOUTER and then get the pattern back and see how the pattern has been affected. So this can it can almost generate maps of where the faults are happening. So there's a Python script that has some of that mapping done. It's a little tricky due to the fact that you tend to hit like word lines and stuff like that. So it's probably not giving you exactly what you want in terms of like a really nice picture. But it gives you a pretty good idea, right? You can get down to either corrupting a few thousand bytes of memory, all the way up to corrupting about half the memory, depending on the pulse sizes. So these two targets are there to sort of help you understand what your faults are doing with the ChipSHOUTER as you're adjusting them. So let's look at the rest of the boxes here. So some of these other boxes, we have this interface box, which has a SMB to SMB cable. So these are some triggering cables. And one of the more interesting ones are these oscilloscope probe monitors. So I'll talk about those first. What these are basically is you have a cable here that plugs into one of two ports on the front of the ChipSHOUTER. And so you can see those ports here and here. This is basically a sort of a separated oscilloscope tip, where half of the oscilloscope probe is actually built into the front end of the ChipSHOUTER. So the idea of this is that if you want to be measuring the pulses generated, you don't want to be risking exposing yourself to really high voltages. And so this probe makes it really safe to do that, because the high voltages are only inside this unit, and what you have here is the divided output. But it's built into an oscilloscope probe cable, so you have a properly compensated cable to connect to your oscilloscope. So once we power up the ChipSHOUTER, I have an oscilloscope here just so you can see that sort of stuff. We also have, so the hardware trigger input is this SMB connector in the back, so there's some adapters to connect various things to that. And I'll talk about that in a minute, actually, once we power on the ChipSHOUTER, to talk about how you might actually be using those. We also have move this out of the way. This is our interface cable. So it uses RJ12 cable, as well as a little isolated serial adapter. So this little adapter here basically allows you to plug the ChipSHOUTER into the computer over micro USB. So we'll pull that out. And the final thing, let's move this out of the way for now. The final thing we've got is this this case here. So you have like a right angle SMA adapter. This is basically used if this is ever mounted in such a manner. So if you need to mount this on a XY table, you could either mount it vertically like that, right, and scan it along. Alternatively, you could mount it horizontally, which has sort of the advantage of it's not taking up as much vertical space, and you might need the right angle adapter to connect it in that manner. So there's just a few probe tips to help with that. There's also, so I mentioned the air inlet, so there's the adapter for where the air actually goes into the devices through that. But the final thing that's of interest really is these probe tips here. And you basically have 4 probe tips. So there's a wider, oops, let's open this up. And they're ranked by the width of this interior coil here. So this ferrite core in the middle. So it's either 4 millimeter in that case, or like 1 millimeter in this case here. So you have 4 1 millimeter coils. And basically what you have is the types of pulse uses you get actually varies based on, the size of the coil. And you have 2 winding directions. So you have either counterclockwise or clockwise winding. And basically if you imagine the right hand rule, if this was like the ferrite, right? If we have a winding going one direction, we get a magnetic field with a certain effective polarity. If we have the winding going the other direction, we get the opposite polarity. So this is going to give you two different voltages injected into the target. So in order to use this stuff, let's pull out the power supply here, and that should be enough for now. And what I'm going to do is I'm just going to show you it powering on. So if we connect this in, so we just have a power supply here. And you'll notice the ChipSHOUTER power supply, there's a little note on the supply, so you always know that, this is what it's for. I hate having, multiple power supplies when you're not sure what's for what. So if we plug it in, the status LED comes up right away saying that it's booting, and you'll hear it beep. So you'll see here two LEDs are on right now. One says fault and one says open. What this actually is the ChipSHOUTER detects that there's no probe attached, so it looks for the short that it would expect. And this is for safety. You don't want to risk charging the system if there was no probe attached. So we basically have this safety mechanism that helps ensure, we don't accidentally charge one. So I'm just going to attach it like this for now. And to arm it, we basically hold the arm for a second and then release it. So you'll see that the ready light comes on. And to disarm it, we can just click that again. So we have to hold it for a second and release, and it'll arm, and then again click to disarm. When it arms, there's also two LEDs on the front here. So you can see these are showing you that the ChipSHOUTER is armed. And if you do something like if you were to remove the tip while it's armed, right, what's going to happen once it loses contact is it's going to cause a fault condition. So to clear this fault condition, now that we're in a fault condition, we can use the serial port to do that. But I'm just going to hold this down, and we have to hold the arm button for some time to clear the fault. There we go. And that's basically to teach you a lesson not to remove the tip. Now, if we just want to do a basic test, I can just hold this pulse button down. And this is actually inserting faults by discharging into this tip here. Now, if we want to see the faults, I mentioned that, one of the nice things we have is there's actually this connected, so let me move some of this stuff out of the way. We have this handy tip here. So all I'm going to do is I'm going to grab one of the scope probe tips I put out of the way. Where'd that go? And we're going to connect this into our oscilloscope. So this puts up, so check the manual, to make sure your scope range is okay. This comes as a 20-to-1 tip at the output here. So you obviously need to check if you're inserting up to 500 volts at the tip, you're basically dividing that by 20. Most scopes can do, like 25 volts okay as an input, but if you have some low cost ones, they may not actually do that. So always double check that. What I'm going to do in this case, right, so I'm going to make sure that the tip here wasn't falling on the cable. So I'm going to plug that into the scope. I'm going to make sure I set my scope range to a high range. And I'm actually also going to specify, because I want to get some vaguely relevant readings here, that I have a probe type. It's set to 2 times right now of 20-to-1. So in this case, I can actually set my scope to have a 20-to-1 probe type. And we're going to trigger on channel 1. And we'll just try that. Okay, there we go. So we can see right away whatever, I don't know what's actually programmed in here. This is just part of the factory test actually. It's inserting 3 pulses in a row. So we can see 1, 2, 3 of these pulses that are actually happening on the target device. And that's just whenever I press the pulse button here. So that's kind of like really basic uses of the ChipSHOUTER. Now, probably what you want to do is you want to actually talk to a computer. And so for that, what we need is we need to take a look at this interface board. So this is pretty straightforward as well. All we're going to do is we'll take our RJ12 cable here. And I'm just kind of avoiding undoing all of the ties. So I'm being a bit lazy with my RJ12 cable. It's just kind of all jammed up. And then I'm just going to plug the USB in to my computer just off screen here, and we'll try to talk to it over the terminal port. So all of this is spec'd in the user manual, so you can also see what the command list is and stuff like that as well. And that user manual is posted on the ChipSHOUTER GitHub. There's a PDF of it there, so you can take a look ahead of time at what that is. Okay. So now we're going to go over to the computer and take a look. So this is not the right serial port. It's probably COM29. Okay. So hopefully we're talking to the ChipSHOUTER. So we see it there. And let's make this look a little nicer by just using the monospace. Okay. So there we go. So you can see I got all of the commands here. One of the notes, the current firmware rev of the ChipSHOUTER, actually there has a bug. I just mentioned it for anyone getting this rev. I'm using Termite that sends all of the command at once. If you use PuTTY or something that echoes every letter as you type, it actually will cause a timeout. So that's just a little side note on making sure you have the right terminal. So you also might have heard it just auto disarmed. It timed out because I wasn't using it. So we can arm it again through the terminal interface. And we can do stuff like, for example, get the pattern trigger. So, or let's just get the voltage. So we can type get, for example, and this actually just gets everything from the device. So all of the settings. And we can see it's set to 481 volts. It's also measured. So the actual bank voltage, isn't always exactly what's set, but it's relatively quick here. We also have a pattern being used for the trigger. So we see this like 111 000 111 000. So how this pattern works, this is basically one of several trigger modes the ChipSHOUTER supports. If we just go ahead and take a look at that guy, what that means is that basically each of these ones represents a certain time step. And this is basically the output state of some driver whenever the device is triggered. So what you kind of expect, right, is to get some waveform that looks like that, and then continues. So if we look, what else was the rest of that? There's more zeros, so I'm just kind of estimating it here, right? And this is actually what's being driven into the MOSFET. So it's important to note that although this is what's driven into the MOSFET, the actual waveform, so if we look back at our scope, you'll notice our waveform doesn't quite look, like that. In fact, the first two look pretty similar, and the third one seems to be tailing off here. So what you're actually seeing happening is this is an artifact of the probe tip itself. Basically has some limitations on being able to actually accept so much charge input. If you attach a resistive load to the ChipSHOUTER, you will see the expected waveform out. In this case, because we're driving this sort of inductive load here, you get some sort of weird effects because of that. Basically, you end up playing around a bit with the waveform to get the desired output. The other thing that we might take a look at too is that, so let's just actually arm that. And for example, I can now pulse it So this is, I'm just running through that terminal interface. And we can do a similar thing through Python API as well. What we could do too is, rather than do the pattern trigger, so if we say get, we're using this pattern trigger right now. So if I say set pat enable 0, what it means is that it's no longer using that fancy pattern trigger. And now when I send the pulse command, it's actually going to look slightly different. Oops. There we go. So we actually see just one big fat pulse coming out of this guy. And what's happening is I'm actually switched to the pattern trigger is generating that waveform. There's a basic trigger mode, which just generates a single pulse of a specified width. So in this case, 160 nanoseconds. The parameters you see here, there's 160 nanoseconds, 10 milliseconds, and 1 repeat. What this is supposed to mean is basically, if we look back at my figure here, this is supposed to be like 160 nanosecond long pulse. There's a certain amount of dead time, and this dead time is very long. Like, this is just used normally if we're doing more ad hoc triggering type stuff. It's then going to insert potentially more of these. So the dead time is the delay between repeatedly sending that same thing, and it's not supposed to be used for like multiple instruction skip or anything like that. The final sort of trigger mode that's of probably most interest, I would say, to a lot of people is actually not using the serial interface, but actually using the on the backside here, there's a little SMB connector, and actually using this connector. So this connector we can set into active high or active low mode. So it's sort of explained in the user manual a little more here. What you basically have, the architecture of the ChipSHOUTER, is that this hardware trigger output is actually directly driving part of the output stage of this thing. So what that means is that you can drive arbitrary waveforms in here from like a waveform generator or an FPGA or something else like that, and that will actually give you your pulse output. And now one thing that's really handy, and this is how I'm using ChipSHOUTER quite a bit, is to actually connect. So we have ChipSHOUTER here with the SMB, and it can be set to active high or active low. So if I'm using it in active low mode, we can actually connect Chip Whisperer. One of these two outputs here, let's move this all so you can see it. This top output here is called a glitch output. And this glitch output, actually what it drives is it drives a MOSFET, and that just goes to ground. It's a very terrible MOSFET, sorry. But basically it's pulling this low. And when this guy is set to active low mode, it has a pull-up internally that's pulling it up to VCC. And so you can basically use the Chip Whisperer to directly trigger the ChipSHOUTER by just connecting, and it comes with the SMA to SMB that you need to do this by connecting this guy over here to this guy over here. You then just need to configure the external trigger to be in active low mode. So as an example, let's go back to my terminal here, and I'm going to plug the ChipSHOUTER back in. I had it unplugged. Plug that back in. Plug my okay, so now I have this plugged back in. We've got the terminal up, and let's reconnect. So what I would need to do is we could set somewhere here, there's a HW trig mode over here. And we can basically set HW trig mode and we could get what it is right now, actually. Oops. Probably mistyped that. Get HW trig mode. Okay, so right now it's active high. So all I'd have to do is set it to active low. So now, fundamentally, when I short that input here, it's going to actually trigger the output itself. So, and it's going to follow however long that low is for. So within the ChipWhisperer Lite, I can now use the existing hardware that can sweep glitch sizes and stuff like that, and directly drive this to give me super accurate timing. The nice thing about that is it's a hardware path internally. This means it's like super low jitter and relatively low delay. So that's all spec'd in the manual if you're kind of curious about what it looks like. But you know, that's just a really quick overview of what's included with ChipSHOUTER. So you get not only the main unit, but the idea is to have all of the sort of accessories, target boards and stuff like that that you need to get started right away. It's also designed, as you can see, to plug into existing equipment. So both stuff like waveform generators and oscilloscopes, as well as ChipWhisperer, and eventually, hopefully, other things within the sort of ecosystem you see. But hopefully this gave you an idea of what's included with the ChipSHOUTER and what it looks like when you get one.